Thank you very much for the nice introduction, and you and your team from the Academy to support and realize this webinar on a very interesting topic called eABR in cochlear implantation using the CI as an electrical stimulator. So eABR provides a wonderful objective evaluation tool of CI function and thus the auditory processing pre, peri, and post-implantation. So if we stimulate the cochlea with electrodes, we are all familiar with some of the first potentials we can evoke, the ECAP, the summed activity of a couple of afferent auditory fibers. And most of you maybe have experience in recording as a far field response the electrically evoked ABRs, the eABR. Here a typical example for the pattern of eABR due to stimulation intracochlear with different current levels. So this is a very interesting tool, and with expanding indication criteria, we also have an increasing clinical interest in eABR measures for this objective evaluation of CI function and auditory processing. So some of the topics of this eABR webinar, Amanda already pointed to some learning objectives. I want briefly point to some physiological basics of eABR. The indication criteria for objective evaluation using eABR are summarized, and the CI-mediated electrical stimulation and recording technique is in the focus of our webinar today. And I will have a look on our setup, the methods, and also the quality assessment we use in our audiological and department and audiological center, Cochlear Implant Center here in Cologne. And I will show you some recordings in small videos so that you get an impression how we do it here, and we evaluate the eABR components and make some interpretation of results. We look for normal clinical findings, pathological cases, and we have a look into the literature, to the clinical significance and the prognostic value of eABR. So we come to the first topic, to the physiological basis. So the first scientist who made an electric stimulation of the auditory system was Alessandro Volta in the 18th century. And he stimulated with two electrodes. Nobody should do it this way. The external ear canal, and then he heard sound. He had an impression of sound, and in his transactions here in the Royal Society of London, he wrote, "It sounded like a thick bubbling soup." So this was the first explanation of what happens after electric stimulation. So we all know, are familiar with the acoustically evoked auditory potentials in the different time domains we can record in the near field with the technique electrocochleography, the activity of the inner ear, sensory cells and afferent fibers of the auditory nerve, and then the far field responses, the early responses, middle latency and long latency responses with the different techniques. We are familiar with it, and if we electrically stimulate with the cochlear implant, then we can evoke the ECAP, the first neural response of a sample of afferent fibers, and then the far field response. This is in focus today, the electrically evoked auditory brainstem responses. They look similar with these components. I will focus on these components today. And we also can record the long latency responses with cortical evoked response audiometry. So we have this evoked activity, and here again, this is the focus of our webinar, in this case, with intracochlear electrodes evoked eABRs with different current units, and you see here the clear morphology of eABR components 2, 3, and 5, and later on more on this topic. So what are our indication criteria for eABR recordings with CI-mediated stimulation, so after cochlear implantation? We have a wonderful tool, eABR, as an objective functional test of the implant and of the auditory processing on the level of the auditory nerve and the brainstem. Yeah? And we can perform eABR measurements as follow-up in difficult cases and functional tests in difficult cases. So low performer, low compliance, young and older children, to get an idea, is the implant working? Can we evoke neural activity at the level of auditory nerve and brainstem? So in other words, can we objectively evaluate whether we can switch the light on in the brain with intracochlear stimulation? So with this technique, we can evaluate the electrode-specific eABR threshold. We have a wonderful support of CI fitting and also of rehabilitation. So we have a verification of aided thresholds. We can compare the activity of in bilateral implanted patients. So we can compare perhaps wave 5s and thresholds of both sides. We can evaluate some side effects. So like facial stimulation, in eABR recordings, we see large myogenic components as such side effects. We can look and evaluate maturational changes. So this is what we want to see. Is there a positive maturation after cochlear implantation over implant use? And also this technique can also be used in patients with auditory brainstem implants, so peri or post-surgery. And some more indications are possible. So we have expanding indication criteria, and we have also expanding need for objective evaluation of what we are doing. And this is the focus of the webinar. So I want to briefly summarize our methods, the general setup, stimulation and recording parameters. So we use here the 2-channel eABR recording with the Eclipse system 4.6, and we use the electrode montage high forehead and IPSI and contralateral must-to-it. This is filter setting. It depends a little bit on the room and surrounding, whether we do it in the operation theater or in other measurement surroundings. We use alternating, so charge balanced B or triphasic pulses. Repetition rate depends a little bit on the pathology, so around 20 per second, and 300 to 500 averages are enough to see clear responses if we have a relaxed patient. So we change the during the or before the recording, we changed the channels. So in the ipsilateral canal, we put the contralateral mastoid, and the control reference is the ipsilateral mastoid. So we record the eABR because of the artifact from the contralateral side. And if we do it, we can evaluate the components 2, 3, 5 from the contralateral side. But in two-channel recordings, I show it later, we can see both channels and we can compare what happens on both sides, also for side effects. So in general, we have two ways of CI-mediated electric stimulation, and this is not often done. I don't know why, but we do it for many years in Cologne. So this is a free field CI-mediated stimulation, or free field eABR. And you have some advantages. You have a functional test with all electrodes active. So a functional test over the full implant on brainstem level. So you can stimulate in free field with a calibrated loudspeaker with clicks, chirps, also speech signals. You can look for early potentials, middle latency or long latency potentials. But today we focus on the eABR, which are stimulated by intracochlear electrodes, and so you activate selected electrodes, you stimulate, as I already mentioned, with B or triphasic pulses, always charge balanced, and here is an example, nice responses with a bipolar stimulation in a cochlear recipient between electrode 11 and 18. So this is a biphasic stimulation. It's a kind of click equivalent stimulation, which was inaugurated by Oliver Jemba, a colleague from Greifswald in Germany, which is published in 2018. So he uses this bipolar stimulation between these two electrodes in contrast to a monopolar where you have different current flows. So this makes sure that you have a current flow through many afferent fibers lying in between, and this is a click equivalent stimulation. And here you see, again, these nice responses, wave E2, 3, 5, at different current levels. So this is a summary of the parameter settings of the Cochlear custom sound Evoked potential software. So again, you have as active electrode, electrode 11. The indifferent electrode is electrode 18, and here is the other parameter setting. He uses a repetition rate of around 20 per second, as I already mentioned. This is also my setting I use in normal 17.3 stimuli per second. So let me shortly say some words about the quality assessment. So in not only in eABR recordings, these are some general recommendations about the quality of measurement. So in objective audiometry, residual noise is the most important parameter. So my friend and colleague Roland Müller from Greifswald, from Magdeburg in Germany, he made this nice picture. So the influence of the residual noise on the recording of auditory evoked potential. So you are, I think, all familiar with it. If you have a very restless patient, you have no possibility, no chance to see near threshold a clear response. So this is visualized here on the right side. You have no idea what is happening here. If you have a restless patient, okay, you get some idea. This could be a shepherd dog or something like that, but you have no idea where is the threshold or the exact evaluation of components is impossible. Only if you have a relaxed patient and low residual noise, you see the clear response here. You can go down near a subjective threshold level. So for click evoked eABR, you go down to a difference of less than 10 or 5 decibel to the subjective threshold. And same holds for the eABR. And here on the right, you see clearly, very clearly, the not the evoked response. This is the cathedral of Magdeburg. So this is very important to have a situation with a relaxed patient in a good environment. And some other words to evaluation of thresholds of auditory or electrically evoked potentials. And here you see a threshold estimation. So colleague Sebastian Hoth clearly pointed out in threshold estimation, 2 measurements must be available in ascending stimulus level sequence without and with verifiable stimulus response. Here you see click evoked ABRs, not eABR, and here you see very low residual noise and a clear response at the subjective threshold level. And you can split the channel or switch on the contralateral canal to look for quality values, FNP values, and something like that. But an experienced audiologist clearly sees here is a response. And so this threshold estimation is of high quality. And this is what we want also in eABR recordings. So our setup and some important general requirements to perform measurements of sufficient or high quality. So as I already mentioned, you need a relaxed patient in a comfortable position. This is very important prerequisite. So you can perform it in a natural sleep, in children, in sedation, anesthetized in the operation theater, or in video sedation in awake state in older children. You need a quiet, well-shielded room with a relaxing chair or bed. You need experienced personnel for recording and evaluation. And this is also important, the correct parameter settings. Here is a look in one of our chambers from our audiological center. And if you start the video, then we can have a small look into our room here. You see the Eclipse equipment and here the relaxing chair. And for children, a video sedation. But it's important to note the video should not be too funny. The children don't have to laugh. They have to be quiet and relaxed. So a quiet video would be the best choice for this. And if we record eABR, CI mediated, you need a certified audiologist, which is a CI specialist. Yeah? If you cannot program yourself the cochlear implant or run the EP software, you need an experienced colleague to manage the software from the distributors to make sure that you have a good CI connection and parameter setting for the electric stimulation. So we have the 4 leading CI distributors, Advanced Bionics, Cochlear, Medel, and Oticon with the Neuro 2 software. And we have for all these cochlear implants the different EP software. So it's the Volta software for Advanced Bionics. But in this software, you need the support from Advanced Bionics, so you cannot run it by yourself. So you have to go into contact to Advanced Bionics, and they can probably manage a measurement with the Volta software. So it's not free available. And the custom sound software from Cochlear, the Maestro software from Medel, and the Digimap software from Oticon, here with the Neuro 2 cochlear implant with a setup with the Eclipse system. So, and here, one of the most important things is the right trigger cable. So always make sure that you have the right trigger cable before you have a patient. So it's really boring if you have a complete setup, patient is there, and you look and search for the trigger cable. Okay. Now I want to briefly summarize the different steps and show some small videos. So very important, the right parameter setting of the Eclipse. So if you start the eABR software with CE-mediated intracochlear stimulation, you have to choose here the, so where is the pointer? Okay, here is it. Okay, the external trigger, yeah? And the system warns you that you stimulate the auditory system with electrical currents. So make sure that all parameters are set properly, the filter settings, number of sweeps, and everything. I will not go too deeply here into detail, okay, select the eABR trigger and use the filter settings, and then go into the EEG window and set the artifact rejection level. In a relaxed patient, it should be around 10 microvolts or less. And here you can activate the stimulus height artifact feature. So this is nice for if you have problems with artifact within the first millisecond, then you can hide it and you can manage very easily the recordings. So the next video shows an overview over the setup. Here you see the Eclipse and the stimulation unit with the Evoked potential stimulation software. Here you see the trigger cable, very important, then the interfaces for the different cochlear implants, then equipment for auditory evoked potentials. And here you see our first volunteer, Pauline. I will introduce her to you a little bit later. I will show you in some small videos now a recording example. And here our first clinical case, Pauline. She's a master of neuroscience, and she is a high performer. So B model supplied a cochlear implant on the left side from Medell at the age of 7 years, and on the right side she wears hearing aids, and with CI only she has a very good performance sentence test in noise, minus 3.8 decibel, and around 90% monosyllables. And let's say hello to Paulina and run the video here. Okay, then we performed for this webinar especially some small videos to show you how to record the eABR. So we have a relaxed position now, and we can go into the next 4 videos. First, we put the electrodes on, prepare the skin behind the right ear, and 20 to 30 times, low pressure. Look at the skin. Don't irritate the skin. Remove fluid. Fix the electrode. And make sure that you have really good contact. You see the electrode montage on the high forehead, and the ground electrode you can see, and the electrode on the right side. And now, next video, okay, the impedance check should be below 3 kilo ohms, and you can change the connections, so make sure that the right mastoid is in the left channel and the left mastoid is in the right channel. Here you see now we remove the cochlear implant and connect the implant with the interface to make sure that we can stimulate with the EP software. First, we have to make a loudness scaling in adults, especially, to make sure that we are in a range where stimulation is heard by the patient. And the next video, video 6, shows after loudness scaling, you can lay her down in a relaxed position, and she has to close her eyes, breathe deeply. Maybe she sleeps in, and then we can set the stimulation parameters. And again, Dirk Fürstenberg, I already introduced him, our Cologne Cochlear Implantation team, a very experienced audiologist. He performs fittings in children and adults for more than 30 years. So he's doing the parameter setting, and here you have the Maestro software. You see here you can choose between B or triphasic pulses. If you use triphasic pulses, you reduce the electrical artifact, and here you see we choose electrode 6, and after our loudness scaling we know the threshold, and we start with a recording sub-threshold. So the next slide, you see the start of the eABR measurement. You check the important parameters. You start sub-threshold. Here you can see at 1 dB sub-threshold level, 2 dB is the first step of current units, where Paulina already announced she can hear. And you see here at around 4 milliseconds, here is a kind of response. And if we go a little further, okay, the next step of current levels. Okay, here you see a clear response. Next step. These are just 300 to 500 averages. And now you see a very clear response, wave 5, wave 3. And if you switch to IPSI and contralateral channel, then you see both responses on both sides. So you can label the peaks E5, go to the next level. After just 100 averages, you see a very clear response, label 3 and E5. And at the stimulation at the most comfortable level, we checked it for the eABR measurement, what is the most comfortable level, and this is the response E3, E5 at most comfortable level. Okay, and within very, very few minutes, you have a complete threshold estimation. Again, go down and check whether for reproducibility, go down here, is this a response which is reproducible? Okay, sometimes wait a few seconds that parameter setting is properly done. Now, this is a clear response near threshold. And last measure, so below threshold, where Pauline said there's no hearing sensation, we performed another measurement. Okay, the video is at the end here, so in the next slide I show you then the results and the evaluation of components. So this is the next step. Here you see the responses from a medial electrode 6, and we saw clearly it was reproducible at here around 400 current unit levels, and at this level it was not hearable. I have to. Now, where is my pointer? Yeah, okay. Okay, here. Okay. Here you have wave 2, 3, 5. This is the contralateral channel, down to 400 current levels. So here on the right panel, you see the split version, so IPSI and contralateral. So in the curves here, you see clearly the wave 2 and the reproducibility of the responses. So this is the evaluation of parameters, latencies E3, E5, the interwave latencies E3, 5, and also the amplitudes. If you split, you can see here the responses and the huge electrical artifact within the first 2 milliseconds. And if you use the hide artifact feature, you can wipe it out, and so you can easily handle the curves and look what is response and what is electrical artifact. Here is the evaluation of responses, wave 2, 3, and 5, and we know it all the absolute latency is shorter compared to the auditory evoked potentials, which are around 1 to 1.5 milliseconds later. So here we see the responses from the apical electrode. In the same way, we performed a measurement, a threshold estimation with 400 down to 300 current units. And here you see evaluation of components of E3 and E5 and the interpeak interval. And here is the comparison of latencies and the amplitudes of the two components for the medial and the apical electrodes. And what you see here, you have significant differences between the amplitudes of E3 and also between the amplitudes of E5 between medial and apical electrodes. So in apical electrodes, this is a common finding. You have higher amplitudes, and I will show later some data from the literature that the amplitude is correlated in some aspects to the word recognition. So this is a significant difference between medial and apical electrodes. So here you see a clinical case, the post-operative eABR recording in a 48-year-old male after 5 years of cochlear implantation and poor performance, monosyllables below 30%. And what you see here is in the intracochlear mediated eABR recording in the already mentioned bipolar stimulation mode, you see clear responses down to a low threshold. Wave E5 is a little bit poor, but you have normal latencies. And in this case, we performed in the free field. No, not in the free field. This is a comparison to the normal eABR waveform in a normal or high performer. So what you can see here is a poor morphology of the more central components of the eABR as compared to high performer or normal performer. So this is a hint maybe on a poor processing on brainstem level. So in the next slide, you see the eABR results from a 40-year-old female after 3 years of cochlear implantation, and she has a very low performance. Speech perception of monosyllables is at 0%, so no speech understanding, no speech processing. And you see clearly wave E3, and you see also clearly wave E5, a little bit poor, but this cannot be the explanation for the bad outcome. So in this case, I performed the free field stimulation. And here you see the results of the middle latency responses for 4 kilohertz, 1 kilohertz, and 500 hertz. Here, threshold estimation for 1 kilohertz, and the middle latency responses are very poor. It's reproducible, but very poor. At 4 kilohertz, you cannot see any response of the middle latencies. And on cortical level, just at 1 kilohertz, it's a kind of idea of a response, but this is a hint to a central auditory processing problem in this patient. And this has impact to the further rehabilitation process, and also on the fitting. That is not a problem of fitting, it's a problem of central auditory processing. So here is again the summary of our finding, the poor morphology MLR and the poor morphology of the long latency responses at the different frequencies. So let's have a look short to the literature. What is the clinical significance of eABR and what are the findings? There is, since many years, some literature on eABR. And as you could see in the data I presented, we have differences between apical and basal electrode. So Gordon in 2007 summarized the results of eABR in children with cochlear implants within the first 12 months, 50 children. And we see significant differences between apical electrodes, here the wave 5 amplitude, and the basal electrode. Here you see the differences also in latencies between E5 in apical electrodes and basal electrodes. So higher amplitude and shorter E5 latency, this is a common finding. And here you see the eABR in children within the first 12 months after cochlear implantation. And what you see is that the latency of E5 in apical electrodes and basal electrodes is decreasing. And also we see here effects in the amplitude. The amplitude is increasing after cochlear implant use. Here you see the time course of E5 latency change during implantation within the first 12 months. So this is the latency of the different components. And this is what we want to see: maturational progress, positive maturational progress during cochlear implantation. So here the summary again, the decrease of wave and interwave latencies with implant use, so predominantly at the central level E5, and which is reflected in the E3 and E5 interwave latency. So in a retrospective evaluation of eABR in adults and children, Lundin et al. Found also some typical findings. They used a classification which was introduced by Gibson with a score of eABR pattern. So 0 score is no ABR visible, and here the components 2, 3, and 5. And so score 3 is the best score, and we looked for the score in these patients and also to a correlation to word recognition. And here you see the correlation between word recognition and the E3, E5 interpeak latency in different frequency regions. So they use electrode in low frequency, mid and high frequency. And here you see the great variance of the data, and you only have a poor correlation because of the spread of the data, which can be seen. And in summary, they said, relying on the score, a negative eABR always predicted a negative outcome. This is an important finding. So the qualitative characterization always allows to predict a negative outcome. And an absent eABR is always correlated with unsuccessful CI outcome. And in this study, they could see no correlation between eABR waveform score, interwave latency 3.5, the wave 5 latency, and MS word score because of the high variance of the data. And last paper, Kubo et al., they made a retrospective evaluation of eABR in postlingual deafened adults. And what you can see here is that we have a correlation, a significant correlation between consonant recognition score with amplitude growth here of the wave E5 and after 1 month after CE use. So these are data after 1 month after cochlear implant first fitting, and a slight correlation between thresholds or lower threshold point to a better consonant recognition score. And in a last paper, which I would like to present, Lammers et al., they found a delayed eABR in late implanted prelingually deafened adults. So if we compare the results of the eABR measures in prelingually deafened or postlingually deafened, so the responses are clearer, the E5 latencies are shorter, and here you see the correlation between CVC score in pre- and postlingual deafened and late implanted. Then we have here significant differences. So E5 latency and E3, E5 interwave latency was significantly delayed in late implanted adults. So these are typical clinical findings which may help you in the assessment of your own data. And so I come to the summary and conclusion. The CI-mediated eABR measure is an increasing and very useful tool for the objective evaluation of CI function and auditory processing of the central auditory system up to the brainstem level. So again, the indication criteria here, we can use it in children, uncooperative patients, unclear poor outcome, in challenging cases. I could show you some interesting data on auditory synaptopathy, on neuropathy, in malformations. And the clinical use is the evaluation of electrode-specific thresholds, the auditory processing on brainstem level, evaluation of side effects. With our data, we can support the CI fitting and also the rehabilitation process. So the prognostic value is, there seemed to be a correlation of eABR parameters and outcome. The morphology, especially the central components, E5 latency, the E5 amplitude, and the 3.5 interpeak latency seem to be correlated with outcome. And we have some variance in the data, but this is a common finding. So we have an increased quality of fitting and rehabilitation programs when we use eABR results. So further evaluation of eABR parameters should be performed in prospective studies. And okay, and at the end, I want to thank especially Dirk Fürstenberg, Pauline, and Pascal for their support and co-work. I want to thank the team of the Audiological Center of the University of Cologne. We implant around 100 patients per year. And I want to thank Interacoustics for realizing this webinar and support. And you all, I thank for your attention and participation. Thank you very much.
Massive thank you to Dr. Martin Walger today for such a fantastic webinar that I know he has put a lot of work into putting together, and it's absolutely amazing to see those videos showing us really every step along the way of performing the eABR test. So thank you an awful lot for your time leading up to today and also for today. We will take a few questions now to Dr. Walger. So first I have for you, can you kindly tell your opinion on using eABR as a tool for balancing of two implant inputs in the case of bilateral cochlear implantation?
Yeah, it's an interesting tool to really make an objective balancing based on E5 threshold and also based on E5 latencies. So with this tool, you can make sure that that both sides are equally balanced. But always you should perform subjective methods for plausibility, so loudness balancing between both sides.
And we have another question here: do you see any advantage of using triphasic pulse over biphasic?
Yeah, using triphasic pulses, according to a BAMA publication, you reduce the electrical artifact.
And we have another question here. Is it enough to perform eABR testing on 3 electrodes, so basal, medial, and apical, or do you need to check every active electrode?
No, I think 3 electrodes would be sufficient. So it's too time consuming and not good for the patient to measure 1 hour or longer. So 3 electrodes would be okay. Basal, medial, and apical.
Absolutely. And on that topic, is the amplitude of the apical greater than the basal? And if yes, why would that be the case?
Yeah, it's a common finding that the amplitudes of apical electrodes are greater, bigger, because of the amount of surviving afferent fibers. So in the basal turn, because of the high frequency hearing loss and the degeneration of afferent fibers, you have lower amplitudes. This is a common finding.
And we have a couple of questions about electrodes. So are you using a 2-channel setup? And if yes, where is the second electrode placed?
Yeah, I always use the 2-channel eABR recording. And as you could see in the video and in the setup, I use the contralateral side on the ipsilateral channel and the contralateral side on the ipsilateral channel on the contralateral side. So this makes sure that you can evaluate your eABR parameters with the software. You can label E3, E5, and so on. So this is the normal procedure that you record the contralateral eABR because of the CI artifact.
Fantastic. There is a question about ANSD. So what sort of eABR findings do you see in patients with auditory neuropathy, specifically children? Obviously, this is a very big topic, so it's probably another whole webinar in its own right, but could you give us a brief insight into auditory neuropathy and eABR?
Yeah, the common finding is present otoacoustic emissions and absent or pathological altered auditory evoked potentials, click ABR, and in eABR measures, you can objectively prove that you induce a synchronous activity in the auditory system, the auditory nerve, and in the auditory pathway on brainstem level. And I don't have the data to clearly state that there is a difference between auditory synaptopathy or neuropathy, but there are data in the literature that in cases with neuropathy, the eABRs, especially from the group of Gibson, the eABR show poorer morphology, longer latencies, and this is correlated to poor outcome. But always, this is not a contraindication for the cochlear implantation. It shows that with a cochlear implant electrode, you can induce a synchronous activity of the auditory system in synaptopathy and also in neuropathy cases. And you see some differences between synaptopathy and neuropathy cases.
Excellent. We have a couple more questions before we will wrap up for today. Some about which current level do you start with? And there was another question on the same topic. See if I can just find it. Yes, what pulse width and current level would you recommend to start the testing?
Yeah, the current level should always be sub-threshold. So if you have the data from loudness scaling, then it's very easy. You know where sub-threshold level is. There you should start. And if you have uncooperative patients, then you need the data from intraoperative ECAP measures. So you should make sure that you start below ECAP threshold level. Select an electrode and start. And I think it's not so time consuming because if you perform the eABR measures, you need only a small number of averages to get a clear response. And the pulse width I used here in my clinical example was 40 microsecond. You can increase it up to 100 microsecond. So this has great importance on the load of the cochlea and the current units you choose in your EP software.
I think we will wrap things up for there. I'm conscious of time, and thank you so much for taking the time to answer so many questions. Thank you to everybody who has joined us today. I hope that you have found the session as useful as I have. It's been an absolute pleasure and an honor to have Dr. Walger with us today. I will hopefully see you all again soon for another Academy Live event. Thank you so much for your time today, and I hope you all have a wonderful rest of the day.